Hi, my dear students. Very good evening. So, welcome to ACE Engineering Academy. Our ACE Preparation League welcomes you each and everybody, my dear. So, in yesterday's class, we have discussed the preparation strategy for our GATE examination. In this today's session, we are going to discuss some important concepts in our discrete structures, right? In our discrete structures, you know that we have the four modules like mathematical logic, set theory and algebraic structures, combinatorics, and graph theory, isn't it? So, in all these modules, so what I am going to do is from the second unit, set theory and algebraic structures, usually the students don't feel any difficulty in set theory concepts and relations, basic relations also they can do some level, that's fine. But whereas coming to somewhat advanced relations like partial orderings, lattices, and Boolean structures, in this area they feel somewhat difficulty. So in this today's session, what we are going to do is, so we are selecting the typical concepts like partial orderings, and we are going to discuss partial ordering concepts, my dear. Yeah, let's have a look. This is the definition of our partial order relation. So see this, a relation R on set A, on set A. My relation is defined on set A. Domain is A, codomain is A, R maps from A to A. That is the meaning of that. Many of the questions you saw that a relation is defined on a set, on a set. What is the meaning of that? So a relation is defined on set A or maps A to A is called a partial order relation if it is follows some conditions, right? So if the given relation is reflexive, antisymmetric, and transitive, isn't it? If the given relation is reflexive, antisymmetric, and transitive, then we can say that relation is partial order. Fine? So I hope you remember the definitions of reflexive, antisymmetric, and transitive. Just recollect in your mind, and don't worry, I can also mention here. Sir, here we have reflexive relation. So the reflexive means I can say like this, in a relation, AA belongs to R for all A belongs to A. Or maps A to A is a relation. In that relation, what happens is every element of domain is having reflexive image. 1 is mapped to 1, 2 is mapped to 2, A is mapped to A for all A. If it is possible, then that relation is called to be, what do you say? Reflexive. Fine. Then antisymmetric. So my antisymmetric definition is just like this. Yes, I can write here. So in your relation, if A is related to B, A is related to B, sir, AB belongs to R, and B to A also belongs to R, then A must be equals to B. And it should be happen for all AB, any order pair. Isn't it? Sir, my antisymmetric definition is just like a conditional statement. If AB belongs to R and BA belongs to R, then A must be equals to B, right? You know the meaning of conditional statement. So in this conditional statement, we can say if clause, this part is just like hypothesis, my dear. Hypothesis. Yes, I am introducing math logic here. Yes, hypothesis here. And this part is something called consequence. Isn't it? Sir, what is your hypothesis? My hypothesis consists two subconditions. A to B exist and B to exist. Both should be satisfied. You know that meaning of that word and. As you are a programming student, and so there are two subconditions. right? Yeah, I want to say some example like this. So you just proposed something like, yeah, there is a condition. The condition is in such a way that if the student cleared his BTech exam and if he qualified GATE, then that student can do masters, right? Sir, this is the conditional statement I have. In hypothesis part, I have P and Q. Yes, the student must clear BTech. He has to pass all papers, whatever papers he has. He has to clear all his papers, and then and he also qualify in MTech entrance examination. Let us suppose GATE is the only chance to do MTech. Let us suppose, just an example manner. So if he cleared BTech and also he qualified in GATE, if he satisfy both conditions, then he can do masters, right? There are some students, let us suppose, there are some students, they cleared BTech, yes, they got very good percentage, they cleared BTech, they satisfied this condition, but they didn't qualified in MTech entrance examination. Then according to this conditional statement, don't go for general way, my dear, I am talking about conditional statement. Let us suppose in this way. So according to this statement, if the student didn't clear GATE, then he cannot do MTech, right? And some other condition, something like this. Sir, a student is here, he got very good rank in GATE, he got like all India first rank, all India second rank in GATE, right? But he is not cleared his BTech paper, some paper is left in BTech, then in that case also, he cannot apply for GATE, he cannot go for masters, right? It's not possible. I hope you got it, my dear. So this is the meaning of conditional statement. Both conditions must be satisfied. If only one condition is satisfied, if AB belongs to R, BA doesn't belongs to R, then you cannot apply what do you call anti-symmetric definition to that particular order pair. The hypothesis is false, na? Isn't it? If the hypothesis is true, then the consequence never be false. You know the meaning of implication. If AB implies R and BA also belongs, AB belongs to R and BA belongs to R, then A must be equals to B. Right? Right? In similar way, let us understand what do you call transitive relation? Yeah, transitive relation. What is transitive relation? The transitive relation is just like a brother relation, right? Isn't it? So in transitive relation, can I say some example in this way? Yeah. Let us suppose Salman. Salman is brother of Amir. Salman is brother of Amir. And Amir is the brother of Abhishek. Let us suppose. Salman is brother of Amir and Amir is also brother of Abhishek. Then definitely Salman must be the brother of Abhishek, my dear. The brother relation is transitive, isn't it? So can I make it in a generalized way? So what is actual definition of transitive, my dear? Yeah, it is also conditional statement like if A to B relation exists, AB belongs to R and BC belongs to R, then AC must be belongs to R for all A, B, C. Yes, in all examples it must be successful. Sir, it satisfied 99 examples out of 100, only one example failed, sir. No, not at all allowed. For all A, B, C, you know the meaning of this powerful quantifier called for all quantifier we have, isn't it? So for all ABC, if you take any pair of elements like A, B, C, for that triplet, if A to B exists and B to C exists, then A to C must exist, right? So if the given relation satisfies all these three conditions, what do you say? Reflexive, antisymmetric, and transitive, then we can call that relation as partial order, my dear. Partial order. So the example for partial order, let me take in this way. R maps A to A. This is the given relation, and A is a set of A, B, C. The domain A is a set of A, B, C, and R maps A to A to A, B to B, C to C, A, B, B, C. Right? What do you say? Sir, A to A to A, it is reflexive, sir. B to B, it is also B to B, C to C. So A to A exists, B to B exists, C to C exists. For every element of domain, there is a reflexive image. It satisfies reflexive condition. That's okay, fine. But whereas coming to antisymmetric, for antisymmetric also, A, B, B, C, C are the successful examples. Whereas coming to AB and AC, I cannot apply antisymmetric definition completely. Only AB present na, we cannot apply. Only BC present now, we cannot apply. Okay. Now, what about transitive? Sir, transitive means, so, sir, no problem with AA, BB, CC, they are the successful examples for transitive, they can hold the condition of transitive. But if you take AB and BC, AC is required, na? AC is required. AC is missing. So, the given relation, whatever I have taken, the given relation is reflexive. Yes, sir, it is reflexive and it is antisymmetric. But it is not transitive. Okay? Yeah, let us take one more example. Here I want to take one more example. A is here. A is a set of 1, 2, 3, let us suppose. And R maps A to A. And the relation is like this: 1, 1, 2, 2, 3, 3. Right, sir? 1, 2, 2, 3, 1, 3. Now you can observe this relation is reflexive for every element of domain. It is having reflexive image, and it can also holds good your antisymmetric condition. Antisymmetric successful examples are like this: 1, 1, 2, 2, 3, 3, right? And 1, 2, 2, 3 requirement is 1, 3. Yes, it is also holds good for transitive property. The given relation is reflexive, antisymmetric, and transitive. So I can confirm that this relation is partially ordered. Okay. Now it is partial order, my dear. The given relation is partial order, and how this relation is framed. This relation is whatever we derived from set A, right? The set A is known as poset, my dear. So that is poset concept. Poset means poset is a set. Poset is a set which is partially ordered. So a set A with the relation R which is partially ordered together is known as poset. Yes, A is a poset, and from A we can derive a relation called R, and that R is partially ordered relation. The R is partially ordered relation and the set A is known as poset. Is it clear? Yeah, let us see some more examples on these partially ordered relations and posets. Now I want to take a small example. Yes, I want to take D6 set with relation divides. Right? My set name is D6. D6 refers to set of divisors of 6, right? Divisors of 6 and relation name is divides. Yeah, let us understand this. Sir, the relation D6 is set of 1, 2, 3 and 6. Sir, I am taking divisors of 6, factors of 6, right? So these are the divisors of 6 and the given relation name is which precedes to divides. Divides. The symbol is just like a vertical line. Divides. Okay. Now I have defined a relation R maps D6 to D6. As I mentioned, the relation is divides. Yes, I want to write the clear relation. The relation is in this way. X is related to, there are two elements just like X and Y in our D6. X is related to Y if and only if X divides Y. Fine. X is related to Y, X divides Y. Yeah, let us make it simple. Sir, we have the relation with D6 here. Let us take D6 set. Divisors of 6, 1, 2, 3, 6 in this way. And my codomain is also D6 here, just like 1, 2, 3, 6. Let us make the relation. X is related to Y if and only if X divides Y. Yeah, let us start. We know that 1 divides 1, 1 divides 2, 1 divides 3, 1 divides 6. Yeah, if X divides Y, then only the relation exists. In similar way, coming to 2, 2 divides 2 and 2 divides 6. So I am not taking the edge between 2 and 3, my dear. There is no relation between 2 and 3 because 2 doesn't divides 3, right? 3 is not divisible by 2. So 2 is not a factor of 3. 2 doesn't divides 3. That's why I am not taking the order pair 2, 3. I hope you are getting the idea. In similar way, 3 divides 3, 3 divides 6 and 6 divides 6. Now let us write the clear relation. Relation is nothing but set of order pairs. Let us write the clear relation, my dear. Here I have a relation. The relation, whatever I mentioned, R maps A to A. A to A is equals to set of order pairs 1, 1, 2, 2, 3, 3, 6, 6. My dear, I am writing these order pairs from this mapping, right? 1, 1, 2, 2, 3, 3, 6, 6. Also 1, 2, 1, 3, 1, 6, 1, 3, 1, 2, 1, 6. Then coming to 3, 3, 3, 3, 6. 3, 3 already I have taken. Let me write 3, 6. And what about 2? 2 is 2, 2 and 2, 6. Right? From 1 I have 1, 1, 1, 2, 1, 3, 1, 6. From 2 I have 2, 2, 2, 6. From 3 I have 3, 3, 3, 6. From 6 I have only 6 to 6. Now, so you can write in any order, no problem at all. So my intention is I want to show that if you observe the given set consists the elements like this, my dear. Yes, here we have the elements. The set of divisors of 6 is It is all 1, 2, 3, 6. Every element is having the reflexive image. You observe here 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3. I hope you are watching this. And 6 is mapped to 6. Every element of domain is having reflexive image. Because of this reason, the given relation is reflexive. And all your reflexive images, whatever you said, they can follow your anti-symmetric property also. If A is related to B and B is related to A, then A must be equals to B. I can suppose the 1 element is here and this is A and this is B, and next time the same element I can repeat. In a set you can repeat the element, right? The relation is also nothing but a set of order pairs. So 1 you can take 2 times, and A to B and B to A, and A is equals to B. So that is the reason why reflexive image is going to be successful example for antisymmetric condition, right? So A to B exists and B to A exists, so the A must be equals to B. Then 2, 2, 3, 3, 6, 6. These are successful examples. Whereas coming to 1, 3, 1, 2, in these type of relations, I think you cannot apply antisymmetric definition. When you can apply, let us suppose if you have something like 1 to 3 exist, and if 3 to 1 also exist, then you can speak, sir, 1 to 3 exist, 3 to 1 exist, but 1 is not equals to 3. This is not an antisymmetric relation. But to say that thing, here you don't have any failure example. Successful examples are there in our hand and there is no failure at all. For these you cannot apply antisymmetric definition, right? So that is the reason why I stressed the definition that much. So you need to follow both conditions, A related to B and B related to A. So here it is 1, 2 you cannot apply for 1, 6, 3, 6 and 2, 6. So these 1, 1, 2, 2, 3, 3, 6, 6, their results antisymmetric successful. So I can say that the given relation is antisymmetric. And moreover, you people can observe it is transitive also. Yes, it is transitive. Transitive definition, A related to B, B related to C, then A must be related to C. Just like brother relation. Yeah, let us think about some successful examples. Sir, here you see something like 1, sir. 1 is related to 3 and 3 is related to 6. I got your point. 1 related to 3, 3 related to 6 means 1 must be related to 6. Yes, it is exist. You can say some other examples also. You can say like this, 1 is related to 2 and 2 is related to 6. Then 1 to 6 is required. Yes, 1 to 6 also exists. I just shown 2 examples and everywhere it is applicable, my dear. For all ABC, if A is related to B and B is related to C, then A must be related to C. It is possible. That's why we can confirm the given relation is transitive. I hope you are getting the things in right way. Now this is another proper example for partial ordering. So the given relation is reflexive, antisymmetric and transitive. Yes, whatever the set you said. Sir, in general notation I written just like R maps A to A. I hope you understand. Here A means my set name is D6. Yes, just like D6 to D6. Sir, the general notation is like this. The given relation is partial order, then the set A and R together is known as poset. Sir, A is a set. In this question, particularly A means set of divisors of 6. D6 with relation name divides is a poset. Poset partially ordered set. Right? So when the given set is a poset, I hope up to here you got very good idea and everything is clear up to here. Then let us proceed. Let us extend the concept level by level. D6 is a poset. Now we are in this stage. Now we want to construct the poset diagram, right? Yes, sir, the given set is a poset. It is a poset. So the whatever the relation A to R, so R is defined on A R together it is a poset. R is a partially ordered relation. So for that relation, for that set, I am constructing what do you call diagram. The diagram is known as poset diagram. Yeah, let us see poset diagram, my dear. So I want to construct poset diagram for D6 with operation divides, and D6 is equals to divisors of 6, 1, 2, 3, 6, and relation name is divides. Let us start. My dear student, whatever the elements you have in your set, just take the elements as the vertices in the graph. My poset diagram is just like a directed graph, my dear. And that directed graph, you know about graph. Graph is nothing but set of vertices and edges. So in that directed graph, what we have is every vertex represents some element in your given set. Okay, every vertex is acting as element. Every vertex resembles to some element in the given set. Yes, let us take the directed graph. Sir, we have graph in this manner. 1 here, 1. First element is 1. After 1, I want to take the element called 2. When I am taking the second element, I need to examine that element. What is this element 2? How it is related? Sir, 2 is related in such a way that you please observe the relation. There is an element 2 here. This 2 is related by 1 and this 2 is also related by 2. What, sir? What your sense? 2 is divisible by 1 and 2 is also divisible by 2. That is my sense. One more time I can say in this manner just by changing the vocabulary in this way. Sir, 1 to 2 you are talking about. So 2 is related by 1. This is the pair I am talking about. 1 to exist and also 2 to exist. So this is the analysis of the element 2. That element must be clear when you are taking in poset. Yes, let us take it. Sir, let us take the element called 2. When there is a relation between 1 and 2, that relation is represented with the edge, my dear. 1 is related to 2. Always the relation is bottom to top only. So the arrow mark we are taking bottom to top and that arrow mark is also default. Right? You can take it, you may not take it. But actual notation is it is a directed graph. Either you may take it, you may not take it. Everybody know that in poset diagram, it is from bottom to top only. Yes, sir, you examined first element and second element. Now let us take third element, that is called 3. Sir, whenever you are taking 3, just examine that element 3. What is 3, sir? Sir, 3 is here and 3 is, excuse me, 3 is here and 3 is related by 1 and 3 is also related by 3. Right? So I hope you are getting that. 3 is related by 1 and 3 is related by 3. So 1, 3 exists in the relation and 3, 3 exists in the relation, but there is no relation between 2 and 3. So because of this reason, what I am taking is, I am taking in this way, the third element is 3 here. 3 is related by 1, but 3 is not related by 2. Fine. Usually the elements, they don't have the relation. If they don't have the relation, they are at same level. It is not compulsory. They must be at same level. You must take 2 at left side and 3 at right side. These things are not at all compulsory, my dear. The thing is only thing how you are assigning the edge. That's only matter. When you are assigning the edge, which means that the relation exists. If the relation exists, then assignment of edge is available. If there is no relation, then the edge is not allowed between the two elements. Right? Sir, let us take the last element like 6 here. 6 is here. Now see this story. 6 is related by 2, 6 is related by 3, 6 also related by 1. And moreover, 6 related by 6 also. Right? So, yes, 6 is related by 2, 2 is related to 6. I hope you are observing my words in a clear way. 2 is related to 6, 2 comma 6. Or you can say that 6 covers by 2, right? 6 is related by 2, that is also okay, fine. Then 3 comma 6, 3 is related to 6. And in our poster diagram, we don't represent the order pairs like which represents reflexive images, transitive images, right? So reflexive images means 6 is related to 6, no need to represent that. And in similar way, 1 is related to 3, 3 is related to 6. Sir, 1 to 6 also edge required, 1 to 6, no, we should not represent that. Okay? Yeah, what is the exercise we did here? Let us see, my dear, in steps. I want to take it in steps. Sir, here we have Poisson diagram or Hesse diagram. In Poisson diagram, every element if two elements are related, just like if x is related to y, x is related to y, xy belongs to R, then only there will be an edge, from x to y. Isn't it, sir? Yes, if x is related to y, then there will be an edge from x to y. And don't think that, sir, x is related to y, y is related to x. Both not possible, my dear, because the given relation is antisymmetric. If the two elements x and y are different, then if x related to y and also y related to x, if both things exist, immediate question what's going to be trigger in your mind is, according to antisymmetric, if x is related to y, y is related to x, then x must be equals to y. That is not possible. You said that they are two different elements. Then the relation cannot be antisymmetric. If it is not antisymmetric, then it cannot be partially ordered. Fine? So, in that way, you can say that the relation is not a partial order relation. So, because of this reason, observe the second point. If relation exists, then there will be an edge. And don't take the edges, avoid the edges, eliminate the edges. You can take in any manner. Eliminate the edges which represents reflexive property and transitive property. Reflexive property and transitive property. Because we are constructing Poisson diagram, partially ordered relation. So in partially ordered relation, the basic condition is it is reflexive. If it is reflexive, for every A is related to A. A is related, we know that 1 is related to 1, 2 is related to 2, 3 is related to 3, 6 is related to 6. No self loops are required, my dear. And moreover, when you are taking about transitive also, I know that if 1 divides 2, 2 divides 6, 1 also divides 6. So I need to take this edge. So I want to represent the edge like this. But according to the rule of Poisson diagram, in your Hesse diagram, no need to represent that edge. Not required. So don't take that edge. So I hope you got the idea about our Poisson diagram. In similar way, we can go for next example. Now my next question is divisors of 12 with operation divides. Construct the Poisson diagram to this. So you can examine the given relation is partially ordered and you can think that yes, it is possible or not. Yes, is it possible? Is it partial order relation or not? And if it is partial order, then construct the Poisson diagram. I hope you can do this. Yes, sir, come on, let us take D12. Sir, D12 means divisors of 12. 1, 2, 3, 4, 6, and 12. These are the divisors of 12, right? Now let me take first element. Sir, our first element is 1 here. And second element is 2. 1 divides 2. Next 3. Sir, 3 is divisible by 1, but 3 is not divisible by 2. Let us take 3 here. Sir, what is the story of 4? 4 is related by for D12, D48. My interest is D48, my dear. Divisors of 48 with operation is, yes, I can take in this way. This is 1, sir. First element is 1. Yeah. Next, I want to take second element 2. 1 is related to 2. And next is 3. 1 is related to 3. Then 4. 4 is related by 2. Yes, students, let us continue. So I have taken up to element 6 and then let us take 8. Let us take 8 now. So 8 is divisible by 4 and lower bounds. And next coming to 12. 12 is divisible by all the numbers except 8. 4 also divides 12. In the same manner, 2 also divides 6. Then we have 16 here. Yes, let me take 16. 16, let me take 16 this side. I have elements like 16, 24, 48. Yeah, let us remember that. I want to take in this way. Sixteen, 16 is related by these numbers, and 24, 24 is related by all the numbers except 16, and last element is 48. 48 is related by 16 and its factors, and 48 is also related by 24 and its factors. Now, this is the Hasse diagram I got, right? In this Poisson diagram, now I want to examine the bounds. Okay, yeah, I want to focus on bounds, my dear. Now I want to take is something called upper bounds. Yeah, let us take upper bounds. So the upper bounds of, let us select two elements just like 2, 3. What are the upper bounds of 2, 3? My dear, when you are taking upper bound, so you should think element in such a way that how they are related. 2 here, 3 here. So 2 related in such a way that 2 is related to 6, 2 is related to 4, 2 is related to 12, 2 is related to 4, 8, 2 is related to 24, 2 also related to 16, 2 also related to 48. I hope you are imagining all order pairs with 2. And in similar way, there is an element called 3 and you can understand how 3 can be related. 3, 6, 3, 12, 3, 24, 3, 48. So 3 related in this way. So among all these upper bounds, what is the least upper bound we can discuss. So what is the upper bound of 2, 3 means? So commonly they are related to something. So you just think in this way, my dear. So 2 is related to something called x and 3 is also related to some x. I want that x. Is it fine? Yes, come on. The upper bounds of 2, 3 are 2, 3, 2 related to 6, 3 also related to 6, isn't it? 2 is related to 6 and 3 is also related to 6. Yes, 6 is one upper bound and in similar way I hope you can guess 12 can be next upper bound. One more upper bound is 24, my dear. Then the common multiple of 2, 3 is 48. Yes, sir, I got your point. By using division, I can understand the relation. 2, 3 commonly divides 6, 2, 3 commonly divides 12, 2, 3 commonly divides 24, 2, 3 commonly divides 48 also. But among all common multiples, the least common multiple is 6. Among all upper bounds, the least common, the least upper bound is 6, my dear. So can I write in this way? The least upper bound of 2, 3 is, it is represented with join symbol 2 join 3. is nothing but 6. Yes, yes, upper bounds can be many, but the least upper bound is unique. Join is unique, my dear. You can say it as join or supremum, different vocabularies we have. Fine. Yeah, sir, we have just taken 2, 3. Let us proceed in the same way. So I want to take some element called 4. Let us examine. What is 4 join 6? What is 4 join 6? Sir, 4, 6 commonly divides 12. 4, 6 commonly divides 24. 4 and 6 commonly having the common multiple like 48. So, 4 and 6, 12, 24, 48. But the least common multiple, so the least upper bound is 12 only. Sir, you already written a symbol called join, just like our symbol. Join means you just write only one number. Don't write 12, 24, 48. I can understand 12, 24, 48, they are the upper bounds. But the least upper bound is unique one. So answer is only 12. Is it okay, sir? So in the similar way, can I go for 8 join 12? 8 join 12 can be 24. And 8 join 16. Sir, when you have the edge like this, you are at 8. You are at 16 now. So if you want to take least upper bound, I know that 8 divides 8. And I also know that 8 divides 16. Yes or no? 8 divides 8, 8 divides 16. So my intention is 8 is related to 8 and 8 is related to 16. I hope you are getting my point. So I am saying in this way, 8 is related to 8 and 8 is also related to 16. So the least upper bound join of 8 and 16 is 16, my dear. Sir, 8, 16. So shall we try this in this way? 8 with 8, 8 with 24, 8 with 48, 8 with 6, 8 with 3, 8 with 2, 8 with 1, 8 with 48. Yes, I have already taken, I think. So can I try the diagram, total complete diagram? Can I try to cover in this way? Yeah, let us start. 8 join 8 is 8. The given structure follows idempotent property. 8 join 24. 8 join 24 is also 24. And 8 join 48 is 48. I hope you are guessing this. 8 join 48 is 48. 4 join 48 is 48. Sir, anything join with 48 results 48 only. Because 48 is not at all related to anything. 48 is the maximal element. 8 join 6. Sir, here we have 8 join 6. 8 join 6 is 24. 8 join 3, 8 join 3, that is also 24. And 8 join 2, 8 join 2, I think it's 8. Then 8 join 1. Sir, you can just see, sir, 8 join 1 is 8. 4 join 1 is 4. 2 join 1 is 2. 3 join 1 is 3. X join 1 is X only. Anything join with 1 is X only. X join 1 is equals to X for all X. So 1 is the minimal element, my dear. 1 is not related by anything. 1 is related to everything. 1 is not related by anything. Right? So what do you say? 8 join 1 is 8. Okay, sir, that's okay, fine. So this is something called our upper bounds. Shall we focus on lower bounds, my dear? In similar way, can I try lower bounds? My intention is greatest lower bound I want to take. GLB, greatest lower bound. Let me start with upper level. Sir, let us take the elements like 16, 24. Yes, sir, I can easily guess what you are going to discuss now. So you can speak in this way, sir. 16 and 24 are commonly related by just something like x comma 16, x comma 24. I want that x. Isn't it? X 16, 24. Commonly related by 8. They are commonly related by 4. They are commonly divisible by 2. And they have the common factor 1 also. 16, 24 all commonly related by 8 and also 4 and also 2 and also 1. There are two elements, 16, 24. They are commonly related by 8 and also 8 factors. Right? So 16, 24 are commonly related by many numbers like 8, 4, 2, 1. So among 8, 4, 2, 1, the maximum element that is called greatest lower bound. There are many common factors. The highest common factor is 8 only. So can I write something like this, my dear? The greatest lower bound of 1624, the notation is meet. 16 meet 24 is 8. Meet symbol, meet. So in similar way, now this time I want to target some element like 8 and I will try to cover the total diagram. My intention is 8 meet 48, 8 meet 24, 8 meet 16, 8 meet 8, 8 meet 12, right? 8 meet 4, 8 meet 6, 8 meet 3, 8 meet 2, 8 meet 1. I will try to cover everything in the given structure, all areas, right? Yeah, let us start. Sir, what is your 8 meet 48? 8 meet 48, anything meet 48, x meet 48 will be x only. 8 meet 48, 8, 48 commonly related by 8. 8 meet 24, direct edge is there, no doubt. Meet is going to be 8, join is going to be 24. Sir, it is 8. 8 meet 16, 8 meet 16 also I think it's 8. 8 meet 8 is also 8, idempotent law. 8 meet 12, this is interesting. Sir, your 8 is here and your 12 is here. Both are commonly related by 4 and also 2 and also 1. But the highest element which is related is 4. Highest element in the sense it's not about number, my dear. I hope you are understanding in relation. 8 meet 12, so the result is 4. And 8 meet 4, 8 meet 4 is 4 only. And 8 meet 6, 8, 6 meet is 2 I think. 8 meet 3, 8, 3 meet at 1. 8, 2 meet at 2. 8, 2, 8, 1 meet at 1. Anything meet with 1 is 1 only, right? Now, my dear student, understand. So, I discussed the greatest lower bound here. Now, I am asking you people, I want to ask join. Join for some pair of elements, just like AB. Meet your greatest lower bound meet for some pair of elements. Now, are you able to answer the question? Can you say join for any pair of elements? Can you say meet for any pair of elements in the given structure? Let us make it simple. For example, you have 6 and 8. What is 6 join 8? 6 join 8 is 24. 6, 8 meet is 2. That is the thing I am asking. So if I give some xy, can you say join? Can you say meet for any pair? Is it possible with you? Isn't it? If it is possible with you, if your answer is yes, yes sir, we can say join for meet for any pair of elements, then that poset is known as lattice, my dear. Yes, yes. Yes, sir, we have a poset. The poset is A together with partial order relation R. General notation is L. Let me say the definition with AR first. Let us suppose A is the given poset and R is the partial order relation. A poset A with together partial order relation R is known as lattice if every pair of elements is having least upper bound and greatest lower bound. Not for some, not for some, any pair you can take. So LUB exist, GLB exist, join exist, meet exist. Okay, that is the definition of lattice, my dear. So 24 in similar way we can construct, 48 we already did. Now see the definition of lattice. A partial order relation, a poset A with R or some relation, L with some relation with precedes symbol is known as lattice. Every pair of element is having LUB, join is just like this symbol, and GLB, meet symbol is like this, just like and symbol. We should pronounce it as meet. So LUB and GLB is known as lattice, and the representation is in this way. L is given set name, poset name, and this is join symbol and this is meet symbol. Sometimes what happen is, yes, the given relation is a partial order relation and given set is a poset, everything is fine. Join exists. In this relation, join exists for any pair. But whereas coming to meet may not exist for something. Such type of posets are known as join semi-lattices. Got it? Join semi-lattices. Join semi-lattices. Representation is like this, my dear. L here with join symbol. I hope you are focusing on this word semi-lattice. It is not a complete lattice, semi-lattice. It is following lattice condition partially. Next we have meet semi-lattice. Sir, meet semi-lattice means, yes, the given structure is a partial order and the given set is a poset. In that poset L, whatever you say in general notation A or L, in that poset L, so meet exists for every pair of elements. You tell me any A, B, I can say A meet B. A meet B is possible, but join I am not sure. Join may exist, may not exist. Such type of relations are known as meet semi-lattice. Representation is like this. Fine. Yeah, let us take some small example. Now I want to take a relation in this way. My relation is defined on your set like 2, 3, 5, 30, 60, 120, 180, some 360 with relation name divides. This is the poset relation. This is the poset and relation is divides. Now I want to construct Hasse diagram to this. Yeah, let us analyze this. Sir, we have some element like 2 here, then 3, 5. Sir, why are you taking separately? Because 2 doesn't divides 3, 2 doesn't divides 5, which means that 2 is not related. That's why I am taking separately. Next we have 30. What is 30 analysis? 30 is divisible by 2, 30 is divisible by 3, 30 is divisible by 5, which means that 30 is related by all the 3 elements whatever available up to now. 30 is here. Either I may give arrow mark, may not give arrow mark. I hope you understand. Always the relation is from bottom to top only. And 30, after that 60 we have. 60 is also divisible by 30 and its lower bounds. And next I am getting the elements 120, 180. Minimum future expectation must be there, my dear. 120, next 180. There is no relation between 120 and 180. So because of that reason, take 120 one side and 180 another side. Then that will be seems to be good. Yes, sir. 120 is related by 60 and your 180 is also related by 60. And final element we have something like 360. 360 is related by 120 and 360 also related by 180. Okay. Yes, sir. Sir, what is this structure? In this structure, if you observe this, in this poset, so if you take any pair of elements, so randomly take some elements, let us see some elements, something like what is 3 join 120? 3 join 120 is 120. 3 join 180 is 180. And 120 join 180 is 360. What is 2 join 180 is 180. You can say join for any pair of elements, it is possible with you. Yes, sir, we can say join for any pair of elements. But whereas coming to meet, I want to raise some questions like, what is the meet of 2 and 3? What is the meet of 2 and 5? What is the meet of 3 and 5? You may not answer these questions. There is no existence of meet for some pair of elements. Even one pair is there, that is enough. One failure case is enough to say that it is not a meet semi-lattice. Sir, if you take join exists, no problem, but there is no meet, sir. In this case, what you are going to do? The given structure is join semi-lattice, my dear. There is no problem with join. It is a join semi-lattice. So why it is not meet semi-lattice? Because of these three reasons. Okay, okay, sir, this is not a meet semi-lattice. Okay, this discussion is okay. Sir, shall we try to make it as a lattice? Shall we make it complete? Shall we make it as a meet semi-lattice? There is a problem now. What is the problem? So 2 meet 3, 2 meet 5, 3 meet 5 doesn't exist. What can be the meet in this relation divides? Sir, 2, 3, 5, they are commonly divisible by, their common factor is 1 only, right? Their common factor is 1 only. You can take simply 1, sir. You can take simply 1. So, if you take 1, then it will become as a complete lattice. Now, my dear student, what I am trying to say is, the necessary and sufficient condition to make the given structure as a complete lattice is simply set of 1. Yes, up to here it is a joint semi-lattice example only, that's fine. And I am extending that to the previous gate question. What is the necessary and sufficient condition to the following structure to make it a complete lattice means you can just add one more element. 1 is necessary, without 1 it is not possible. And 1 is enough. 1 is sufficient. 1 is necessary and sufficient. I hope you got it. So in similar way, you can understand what you called meet semi-lattice also. Can I take meet semi-lattice in this way? Yeah, now my poset structure is like this. 1, 2, 3, 4, 6, 9 with operation divides. Right? Let us make it. Sir, here you can take 1. 1 divides 2. And also 1 divides 3. And 1, 2 divides 4. Then coming to 6, sir, we have 6 something like 6 is related by 2 and 6 is also related by 3. And next we have one more element called 9. 9 is related by 3 and also 1. Now observe this structure. In this structure, if I ask meet, you can say meet for anything. It is possible with you. Yes, sir, meet is here. What do you say? What do you call the 4 meet 6? If I ask 4 meet 6, 4 meet 6 is 2. What is 4 meet 9? That will be 1, isn't it? 4 meet 9 is 1, 4 meet 3 is 1, 4 meet 2 is 2, 4 meet 1 is 1, 4 meet 6 is 2. You can say anything meet possible like this. But whereas coming to join, join is not possible, my dear. Yes, I want to raise some questions like, what is 4 join 6? What is 4 join 9? What is 6 join 9? What is 2 join 9? What is 2 join 9? What is 3 join 4? You cannot answer these questions at this level because it is not available in the given structure. Because of these reasons, I just put question marks here, doesn't exist. Because of these reasons, it cannot be joint semilattice. It's meet semilattice, that is okay, fine, but it cannot be joint semilattice. Now, in this situation, can I ask some question like, what is the necessary and sufficient element? What is the necessary and sufficient element? Maybe one element or some set of elements. What is the necessary and sufficient to make the given structure as a complete lattice? If I raise such questions, what do you say? So, 4, 6, 9, something like, they commonly divides 36. 36 is necessary and moreover 36 is sufficient. Right? Now, if I take the structure like this, now this structure become as a complete lattice, my dear. Now it is a complete lattice. Got it? So the join semilattice and what do you call meet semilattice? I hope you got a clear idea. If the given structure lattice follows both conditions, join semilattice and meet semilattice, then you can take it as a whole lattice, complete lattice, and it should be bounded. Maximal element, minimal element, maximal element must be there. Fine. So that is about our lattice discussion, and now I need to discuss. Yes, here we have the clear definitions. You can take some snapshot of this, and you can take some screenshot, and you can take the definition if you want to take it in clear way. I already discussed this, and I want to go for the complements. Sir, what is meant by complement in a lattice? In lattice, we have the complements. A and B are said to be complements if A join B is a maximal element and A meet B is equals to minimal element. Whoa. What, sir? There are two elements just like X and Y. So X join Y must result maximal element capital I. And X meet Y is equals to minimal element O like. So if it happens, then we can say that two elements are known as complements, my dear. Yes, we can call them as complements. So shall we try some complements in the given structures? See my first example 2 here. Sir, in this question, if you observe this, 2 join 3 is equals to 6 and 2 meet 3 is equals to 1. Yes, then you can say both 2 and 3 are complements to each other. The complement element of 2 is 6, 3. 2 is 3 and the complement of 3 is 2. Okay, 2 and 3 are complements to each other. Now I want to take one more example here. Sir, we have D12 here. In this D12, we have the elements like 3, 4. So if you take 3 join 4, the 3 join 4 results the maximal element, that is called 12. And 3 meet 4, 3 meet 4. Can you guess 3 meet 4? What is 3 meet 4? 3 meet 4 is one minimal element. Then we can say that 3 and 4 are complements to each other. They are inverse elements to each other. It is not necessary, my dear. In the lattice, element should have the complement. Every element need to have the complement. So it is not at all required. Some elements may have the complement. Some elements may not have the complements. Sometimes there is no complement at all. But still the structure is called lattice. The requirement is only one thing, like join and meet must exist for every pair of elements. Right? Okay, so they are the examples for the complements. And I think in this structure, can you guess what are the complements? Right? 16 and 3, na? If you take 16 and 3, so can I write like this? 16 join 3. 16 join 3 is equals to 48, maximal element. 16 meet 1 is equals to 16 meet 3, na? Yes. 16 meet 3 is equals to 1, that is called minimal element. Both conditions must be satisfied, not either or. Then only we can call them complements. Okay? Yeah, that's fine. So I hope you understood the definition of complement. And now my discussion is about something called some complement question. So this is the question I have. What are the complements of element A in the following lattice? Right? So I want to draw a structure. From this structure you should say what are the complements available and everything. Yeah, let me take structure in this manner. So this is maximal element, sir. Let us suppose maximal element here. Like I, minimal element O, and this is one element A. That is my question. And this is B. This is some element C, D, and E. Now my question is, what are the complements of element A in the following lattice? In this structure, what are the complements? Sir, remember complement definition. So the complement definition just now we discussed, if x join y is equals to maximal element and x meet y is equals to minimal element, then we can say that x and y are said to be complements. Sir, if you observe this, here we have A is here, element here. Let us examine element A. Let us operate with some other element. You can take any element, sir. A join B. What is A join B? A here, B here. A join B. Yes, relation is not there in your hand, but Poset diagram is clearly available. Na? You can say A, B, join will be I. Yes, join is I. I hope you are observing the diagram. And in similar way, A meet B. A here, B here, meet, both are related by O. No other common element, only 0 or O you can say. Sometimes the representation can be 1 and 0. Sometimes they can also take I and O. These type of notations we have for maximal element and minimal element. Right, sir? A meet B here, so that is O. So I can say the complement of A is B. Right, sir? The complement of A is B. Now, I want to elaborate the thing in this way. Here, element I want to take, and here I want to take corresponding complement. Now, let us start. A here, element A complement is B, and also C. I hope you can guess that AC. A, C, D and E. There are 4 complements for A. This is previous gate question, my dear. I think for 2 marks they asked this question. Sir, this question is okay. Let us extend the solution to understand more concept. So, sir, complement of A is B, C, D, you know? Okay, that's okay, fine. Can I ask you what is the complement of B? Complement of B can be A, also C, also D, and also E. And complement of C is, C element complement is A, B, and E, I think. A, B, and E. My dear student, you observe one thing. Whenever I am taking the complement of C, I take an A, B, and E. Why don't I take D? Why D is not complement of C? Sir, when you are taking the complement of C, if you want to examine C and D together, CD join is C, sir. CD join is C. But we want CD join I, right? I, right? Maximal element. CD join is not I. That's why C and D cannot be complements to each other. Not only join, you can say about meet also. CD meet should be D, na? Here we have D. But according to complement definition, the meet should be like O. But CD meet not O. Because of that, I didn't take complement of C is D. So let us take something called D. D complement is A is one complement and B is one complement. D and B are complements to each other. That is my intention. And D and E are complements. And in similar way, A, B, C, D I covered. Let me take E. I think for E almost everything is complement. A, B, C, D are complements. So last but not least, complement of I is 0. 0 or O, whatever you say. My dear, you observe the given structure. In this structure, every element is having the complement. A is having complement. It may be unique, may not be unique. That doesn't matter. Every element. A is having complement. B, C, D, E, I, O. Every element is having complement. So when every element is having complement, that lattice is known as complemented lattice, my dear. That is known as complemented lattice. Okay. So in normal, for the given poset, if you want to say the given poset as a lattice, complement is not required. Either the poset is having complement, may not have complement for any element. It can be lattice. That's fine. But if you want to say lattice as a complemented lattice, some other condition what you required is every element in the given structure must have the complement. If every element is having the complement, then that lattice is known as complemented lattice. Got it, my dear? So this is the way of understanding the concepts. So what is a partial order relation, what is a poset, and how to construct least upper bound join, and how to construct what do you call greatest lower bound meet, and what is a lattice and what is complemented lattice, when two elements are said to be complements. All these concepts we discussed in today's session, my dear. And thank you very much for your cooperation. So see you again. Bye. Thank you.